So let me talk about sign of a permutation. So for each permutation, I'm going to assign a sign, a +1 or a -1. And this is going to give you a function called sign from the permutation group to the group with two elements. And I'm thinking of this as a subgroup of multiplicative real numbers. So -1 times -1 is 1, and 1 times -1 is -1, etc. And this is going to be a surjective homomorphism from the permutation group to this group with two elements. And it has a lot of use. First of all, it's very important in understanding the structure of this group Sn. If you want to define the determinant in general, for example, in linear algebra, you have to use this homomorphism if you want to do it carefully. But it's also rather subtle. There are many ways of defining it, but whichever path you take, you have to do some non-trivial work somewhere. So the road that we are going to take is kind of graphical, pictorial, and I think rather intuitive. It sort of tells you why you have this homomorphism or how it works. But to make it completely formal and rigorous, this would take quite a bit of work. What we are going to say can be turned into an official proof, but the way we are going to say it, it's not going to be an official proof. We'll be happy with just giving the idea. So the first thing I need to do is introduce something called graphical notation for a permutation. So far we have two ways of representing a permutation. The original way, called two-row notation, you just write down 1, 2, 3, 4, 5, 6, and then you write down on the second row where they go. So 1 goes to 4, 2 goes to 1, 3 goes to 2, etc. That gives you a permutation of 6 letters, an element of the group S6. And here is a more shorter cycle notation, which we played with for a while. So here is a third notation called graphical notation. To get that, you write 1, 2, 3, 4, 5, 6 in a line, and again 1, 2, 3, 4, 5, 6 below it. And then look here, 1 goes to 4 in alpha, so I'm going to join 1 with 4. 2 goes to 1, so I'm going to join 2 up here with 1 down here. 3 goes to 2, 3 goes to 2. Keep looking, so 4 goes to 6, 5 goes to 3, and 6 goes to 5. And this picture is the graphical notation for alpha. The first thing that this graphical notation does for you is it gives you something called the crossing number. The graphical notation leads to the crossing number. Of a permutation. For sigma leads to the crossing number of sigma, denoted n sigma, which is really the number of times the threads cross. So let's count the crossing number of this alpha. It is 1, 2, 3, 4, 5. The number of times these threads cross. 5. And once you have this crossing number, you can actually define this function quickly. Define this function called sign from the permutation group to the group with two elements plus minus 1 by sign of a permutation is -1 to the power the number of crossings. So more explicitly, this is 1 if the number of crossing is even. It's an even number of crossings, and -1 if the number of crossing is odd. So this one has sign -1. I have another permutation here to play with called beta, and I drew the graph for that just to save a little time. Here it is. I'm going to take it and put it right next to the other one. And just clean up the picture a little bit. So let's calculate the crossing number of beta as well. We count 1, 2, 3, 4, 5, 6. So this one is 6, so it has sign +1. And now what makes everything tick is this observation, key observation is the following: that the number of crossing for the product beta alpha can be calculated in terms of the number of crossing of alpha, number of crossing of beta, and then there's a difference which is always an even number. An even number. And I want to explain why. And this is what makes everything tick. This would imply that this function is actually a homomorphism. Okay. Very quickly. So for that, let me first calculate n beta alpha. So let's draw the graph for beta alpha quickly. One, two, three, four, five, 6. 1, 2, 3, 4, 5, 6. 1 goes to, I've calculated the product already, you can check it. So this means first apply alpha, then apply beta, and you can calculate the product. 1 goes to 2, 2 goes to 3, 3 goes to 5, 4 goes to 4, 5 goes to 1, and 6 goes to 6. That's our beta alpha. Let me also calculate the crossing number. It's 1, 2, 3, 4, 5. I claim that this 5 can be calculated in terms of the top picture. Because the graph, so here's the key observation, that this picture is obtained from the top picture by erasing the part in the middle and then straightening these strings. If you imagine these black lines as strings, you need to just make them taut and straighten them out. And this is again seen rather nicely in an example. So like if you take this string, this string starts at 2, goes to 1, and then goes to 3, and straighten it, you get that string. Okay. Here is maybe another one. You take this string, this pink one, straighten it. It's already straight, this one. So it goes the same way from 5 to 1. So that's one, that the picture for the product is obtained from the picture for alpha and beta, taking the picture for alpha and beta, putting them below each other, and then straightening the strings. And then, when do a crossing up here contribute to a crossing down here? So the observation is that a crossing in the top picture contributes to a crossing in the bottom picture if those strings cross only in one part of the picture and not in the other part. So for example, the blue string and the pink string that I drew, they cross only once. They don't cross in the top part of the picture, but they cross in the bottom part of the picture, here. So they still cross here, you see. But let's take another string. Maybe here's the punchline coming. Here's a blue string starting at 2, and here's the yellow string starting at 1. They cross in the top part, they also cross in the bottom part. So when you straighten them, they don't cross anymore, as you can see in the bottom picture. So these, I say, form a cancelling pair. So when two strings cross in both parts, it doesn't contribute to a crossing in the bottom picture anymore. Otherwise they do. So we can count those pairs. Here is a pair. Here's a cancelling pair of crossing. Oops, not that. I'm sorry. This one. Those strings crossed and crossed again. Here is another one. Between the string starting at 1 and the string starting at 3. And here is another one. So these 6 crossings don't contribute to crossings downstairs, but the other 5 do. So like this one gives you this one, this gives you these 4, as you can see, and then there is a 5th one down here which gives you this one. So this 5 is really the 5 from up here plus the 6 from down here, then minus this red 6, which is really 3 pairs. And the whole point is that they come in pairs, so it's an even number. So that's why n beta alpha is n alpha plus n beta minus an even number. This even number is number of these cancelling pairs times 2. Okay. And once you know this, you know that sine is a homomorphism, because now let's calculate sine of beta alpha. It's going to be sine of minus 1 to the power n beta alpha, which is minus 1 to the power n alpha plus n beta minus an even number. But minus 1 to the power an even number is just 1. So it's just minus 1 to the power n alpha plus n beta. So it's minus 1 to the power n alpha times minus 1 to the power n beta, which is sine of beta times sine of alpha. Here we are only talking about plus minus 1, so there is no problem in commuting. And then finally you notice that sine of a transposition is certainly minus 1. But if you draw a transposition as an element of S6, the picture looks like this. So this is the graphical notation for the transposition 1, 2, right? It flips 1 and 2, and then everything else goes to itself. So there is only one crossing. So that gives you minus 1, and sine of the identity transposition is certainly 1, because there is no crossing. Here is 1, 2, and here is the identity. And once you have this homomorphism, that lets you define a very, very important subgroup of Sn called the alternating group. It's the kernel of this homomorphism. Means it's all sigma that have sine 1. Meaning for which this picture, this graph, has even number of crossings. So this one is even. This one is in. This one is in An, but this one is not. This one is in An, but this one is not. This one is also not. You have to have even number of crossing. Yeah, and this subgroup is a very important subgroup of Sn. We'll talk about it a little more next time. It's called the alternating group. Okay. We'll continue.